From WXXI News, this is Connections. I'm Evan Dawson. Our connection this hour was made in the Chilean Andes with a celebration. Video from PBS's Nova shows scientists whistling, dancing, clapping. For some, the celebration was one that was about 2 decades in the making. The team was reacting to the first images captured by the Vera C Rubin Observatory, home to the world's largest digital camera ever built for astronomy. Every few nights over the next decade, the camera will capture images from the entire visible sky. In the Nova video, one scientist can be heard cheering, "Greatest images in the history of astronomy." As reported by WXXI's Veronica Volk, the series of images will create the most detailed time-lapse record of the cosmos ever captured. We're talking about 60 million billion bytes of imagery. They will create a movie of sorts, which will feature exploding stars, colliding galaxies, and scientists hope solve some of the greatest mysteries of the universe, like those related to dark matter and dark energy. Those who saw the images described them as awe-inspiring. Some of the first people to see them were community members in our own backyard. Last month, the Strasenburgh Planetarium hosted a first-look watch party, one of several hundred across the country. Rochester was a fitting location for one of those parties, since one of the mirrors in the Rubin Observatory was developed in Rochester. This hour, we're talking with the experts, including those who worked on the telescope, about the galaxies, nebulas, and asteroids they saw, and what it all means for the future of science research and our understanding of the universe. And I want to welcome our guest now. Welcome to Jim Bader, director of the Strasenburgh Planetarium. Thank you for being with us.
Thank you for having me on.
Next to Jim is Dr. Segev BenZvi, and Dr. BenZvi is an associate professor of physics in the Department of Physics and Astronomy at the University of Rochester. Welcome. Thanks for being here.
Hello. Thank you.
Across from Dr. BenZvi is Dr. Becky Borrelli, and Becky is principal fellow in space superiority and imaging systems at L3 Harris. Welcome to you.
Thank you.
And next to Dr. Becky Borrelli is Dr. Fred Moolekamp. Fred is a research scientist at the Rubin Observatory. Welcome. Thank you for being with us as well here.
Thank you.
So, Jim, let me start with you with these watch parties. What was it like at the first look watch party there?
It was exciting for us, I think, in a lot of ways. It was also it was a first in the planetarium. It was a huge international dome cast. So a lot of planetariums got together and had a base of operations so that we could have a fully immersive event in the theater. And I think that we were really fortunate that Rochester's such a hub. We were able to bring in some wonderful experts and people who have insider views, so we could do a great Q&A to talk about really what's happening with the big release.
Yeah, I mean, it's such a great place, and Jim is right. This really is a great opportunity this hour for us with the guests here, but also in this community to have access to these experts in this moment. And so, you're looking there at twinkling galaxies and these pink nebulas, and is it hitting you what you're looking at? I mean, how is it sinking in with you when you're seeing this stuff?
I mean, definitely. When it hits, that the views of what you're seeing were spectacular, but what was wild about these images is that you could just keep zooming in and keep zooming in. And this is why I think the planetarium was such a great platform for this, because while you could look at these images on your screen, you needed some kind of an app, which Rubin had released to view them. But in the planetarium, you could show them really and a lot closer to their full scale.
No, I mean, amazing is like understating it, because Becky, I've got a friend who has a Droid, like a Samsung phone, and I have an iPhone. And if he tries to send me a video, it's just a blurry mess. For days, we cannot figure out how to solve this problem. And yet you guys did something that allows you to keep zooming and keep zooming and keep zooming in deep space. So first of all, I feel like my friend should be able to solve this Droid problem and actually figure out how to send me video. But second of all, what in the world have you done here? I mean, this is really remarkable. How did L3 Harris get involved?
We were contracted to do the secondary mirror, what's called the M2 in the system. It's about a 3.5 meter sized optic, so roughly 12 feet in diameter. And as most secondary mirrors, it's convex, which means instead of a bowl shape, it's a dome. It's like a hill. And so our job was to grind and polish that mirror to its final figure. And keep in mind when I say that, if we had an error on the order of a micron or less, so take the diameter of the human hair, divide it 1,000 times, it had to be better than that, then they would not be able to get the images that they're getting. So our job in manufacturing these optics is to make sure that they have a pristine surface and are going to be able to perform at the level they're supposed to.
So can I ask you a dumb question?
Yeah, of course.
Now, somebody smart years ago said to me, "There's no dumb questions. Just dumb people ask questions." No, I have a question that, forgive me here, but what you're describing, the level of precision that is required, where was the construction of the mirror happening?
It was happening here in Rochester.
So how do you transport it then?
So even just moving it around our shop, we basically have to shut the shop down whenever it's moving through the shop. Because if you imagine something that's, bigger than, a story of a building, right, is 12 feet in diameter, everybody has to get out of the way. And it's glass. It's fragile. It'll shatter. It'll break. So there's a team of people that are in charge of lifting it off of whatever equipment it's on, putting it on its transport device. And then there's another team that's standing around making sure no one's coming through, no one's in the way. It's a huge effort just to move these things. Typically, when we need to move them between buildings, it's done at night, so there's not a lot of traffic. But we also had a very large steel box that this thing was moved around in.
To me, truly unbelievable. Did you know before the first images came back, did you have a sense that it was going to work the way you wanted to?
We have high confidence. We've
Yeah.
been doing this a long time, but there is always a little bit of a moment of sort of holding your breath, because with any of these systems, whether they're ground-based systems like Rubin or space-based systems like James Webb or Nancy Grace Roman, there's a little bit of holding your breath until you actually see an image and say, okay, yeah, we did our job. Everything looks great. So we had high confidence, as high as we can, but when those images come back, there's a sense of relief and immense pride that we managed to accomplish that.
And before the program began, Dr. BenZvi was just talking about some of what we might be able to start accomplishing or understand better about the universe, literally gravitation, expansion of the universe. Take me through some of the kinds of things that you are excited to see explored.
You should be careful asking that question because I could give an hour-long lecture.
Give me the short version first, and then we'll go deeper.
Yeah, the short version is both of those things are to some extent century-old problems. I mean, this is the cutting edge of physics, but we've known about dark matter for about 100 years. And to understand dark matter, it really doesn't require much more than just high school physics, right? Newton's laws of gravitation. And the idea is starting about 100 years ago, people looked at clusters of galaxies, studied how they moved, and you can use Newton's laws to take that motion and infer how much mass is there. And if you do a careful census, you count up how many galaxies there are in a cluster of galaxies, and you ask how much mass is in each one of those galaxies, because you can estimate the number of stars in them. You get a small fraction of mass from just those galaxies compared to what you infer from Newton's laws. So it's a very huge underestimate. What we can see is not all that's there. And because we can't see it there, it was called dark matter. That was actually a coinage by Fritz Zwicky, a Swiss astronomer in the 1930s. So that dark matter influences the motion of mass throughout the universe, but we can't observe it. We can only observe its indirect effects. And so part of what Rubin is designed to do is by making this amazing catalog, this amazing atlas of hundreds of millions of objects, billions of objects really, we can really start to quantify the effect of this dark matter on the objects that we can see, the luminous matter, the galaxies.
So make sure I'm understanding dark matter well. If I'm in a room with a closed door and next door I hear music of many different instruments flowing out of the room, and it's music maybe I've never heard before, but it's clear that it's different tones and different sounds. And then finally I can get into the room, but it's very dark, and the first thing I find is a piano. And I hear what the piano can do, and then I hear the sounds the rest of the room is making, and I say, okay, the piano is part of this, but this is not the totality of what's creating the sound. Just because I can't see the rest of the instruments doesn't mean that they're not there.
That's right.
I haven't found them yet, but I know that something is going on here. Is that roughly what you're talking about, dark matter?
Yeah, it's a reasonable metaphor. What dark matter does, it gravitates, it attracts other mass, just like planets that we see in the solar system, just like other stars. You know, we're attracted to the sun. We're obviously on Earth. We're attracted to it. And galaxies attract each other, and they cause each other to move. And so we can see that influence. But if you ask the question, is all the mass that's out there just the galaxies? We cannot explain their motion. We need there to be other mass in order to be consistent with the laws of gravitation as we understand it. Now, there's another solution to this problem, of course, which is you throw out the laws of gravitation. Maybe you say Newton's laws are wrong. Einstein's general relativity is wrong. And there are arguments for that, but it's not the most plausible argument, to be perfectly honest. It's not consistent with a lot of evidence that we have from many, many other sources.
We think that certain laws do travel pretty well.
Yes,
right?
exactly.
The law of thermodynamics seems to travel, right?
Yes.
So there's a lot that we might still not know. But do we have any guesses on dark matter? I mean, how much are we getting anywhere close to starting to solve that?
Yes and no. I think a lot of the progress that's been made in the last few decades has been ruling out what dark matter could be.
Mm-hmm.
So people have looked at many things like asking, well, is it gas? Is it dust? And the answer is no. And the reason is because gas and dust can heat up as it moves. And eventually when something heats up, it glows, right, in the infrared. And infrared astronomy has existed since the 1950s. And so we would see that in other wavelengths. We wouldn't see it with our eyes, but we would see it with special instruments. Then people ask, maybe it's things like objects that are called brown dwarfs. Essentially, imagine like rogue planets, things like the size of Jupiter, that are almost massive enough to be stars, but do not have nuclear ignition inside of them. Is the universe filled with those kind of objects? And starting in the 1990s, people did lots of censuses looking for evidence of that. And those do exist, but it's not nearly enough to describe the dark matter.
Okay. Okay, so one other one on this before I turn to Dr. Moolekamp here. So why does Rubin give us a better shot at understanding this? What is going to improve our chances of understanding?
I mean, it's largely the statistics and a view of the universe that's much wider and much deeper than anything we've had before. So by looking at much, much fainter objects, we can study the motions of the universe in ways that would otherwise be biased because we can only see the brightest objects. And every time you go deeper, you're looking at fainter and fainter objects, you learn more. And that's, without getting too technical, that's essentially the gist of it.
So Dr. Moolekamp, you've heard your colleagues in different fields here describing maybe the significance here. When you are talking to the lay public and they say like, well, what is the big deal about Rubin? You know, we've had different devices before that help us see into the universe. What's different this time? What do you say?
I guess the two big buzzwords are big and fast. For something this big to be able to move as quickly as it does, like you have to imagine that this telescope weighs about 500,000 pounds. Okay, and that's if you include the optics, the camera, the mount, all that. And in just a matter of seconds, it can go from pointing in one place of the sky to the other. And it's just going to do that every 30 seconds the entire night. So the amount of data that we collect is just astounding. You know, we're going to generate about 10 million alerts per night of transient objects. So those are going to be things like asteroids, comets, supernova, and distant galaxies. You know, just more data than we can go through. You know, it's going to take us decades to go through all this, right? Because it's going to keep going over the same areas. What happens is every time you image the same place in the sky, you know, there's noise in the background. So you have, you know, kind of like a small signal to noise. And then you take another image, you can basically kind of add those together in a certain way so that your signal increases while your noise stays the same. And that's what allows you to see, you know, further back in time. It allows you to see fainter objects. And so like Segev was saying, so like in terms of like dark matter, for example, what we can do is there's an effect called gravitational lensing. So what happens is if you have like a cluster of dark matter and light goes through it, it actually acts like a lens and bends the light. Even the sun does this. It was one of the first proofs of general relativity was showing that the sun bends light from stars that are nearby it. And so what you can do when you have billions and billions of galaxies now is you can look at the light and you can see how on average their shapes are manipulated and bent. And this is so-called weak lensing. And so by doing that, we can actually have a detailed map of dark matter. And then by other measurements that we can make on the galaxies to tell how far away they are, we can know, you know, kind of like a 3D map of what dark matter looks like.
Maybe it's just because I've been watching Resident Alien, but I'm curious to know, will we have a better chance to see biosignatures if they exist with this?
So this isn't my field. I think you need more spectroscopy for that. And so you could, if you're looking at something like that, then we just have like really broadband filters, as opposed to having like really detailed measurements that you could see individual elements.
See, that's a very honest answer. And I'm amazed at the conversation that we're having here because I'm tying it into what we're going to talk about next hour, which is trying to understand how to use tools and technology in a way that supplement the human experience and doesn't foreclose on the need for human knowledge, human skills, etc. And listeners probably know I'm a bit of a skeptic about AI, although I would not be surprised to hear our colleagues and maybe Dr. Moolekamp, if you are optimistic that AI will at least help with data collection, with sorting information in a way that doesn't remove the need for the human work that's happening. Is AI helping you?
I use it every day.
Every day.
Every single day. And not even just with my work. But yeah, I think if you use it properly, AI helps you expand your curiosity. Like if you're curious about something and you have an idea, you can, normally we would do, like if we're working on something new, we do something called rubber ducking it. And so like you have an idea and you just tell it to your rubber duck and you don't really get any feedback, but just saying it out loud and being able to kind of get the words out helps you get an idea, helps clarify the thoughts in your head. AI is like a rubber duck that also can give you feedback. And so you can say things that like, I can ask it questions that I'd be way too embarrassed to ask Segev because I would like think he's judging me, right? Or like, any of my colleagues.
Never.
But if I, but I can ask an AI because I don't have that judgment. So I can ask it really simple questions that then there may be like some small piece that I was missing so that all of a sudden now my picture becomes so much clearer. And so like all day long, like I use it to, if I'm working on an algorithm, if I'm working on like some data and I am like trying to like kind of fine tune an idea, I find it invaluable.
And you find it pretty accurate, pretty helpful.
It's like talking to a person, right? Like when you talk to a person, you can't trust everything that they say is going to be 100% right. You have to use that logical part of your brain that says like, do I trust this? Let me poke at it a little bit. Because sometimes when you do that and then the AI starts to crumble, you're like, okay, like you've still helped yourself because you're getting a better picture in your head.
Now we're getting into a semantic battle, but I worry about anthropomorphizing AI and thinking it is like a person or giving it, human sounding names. And I understand why we do that. And we're going to talk more about that next hour. Next hour is all about AI and our relationships and what boundaries we draw and, what we expect of technology in the future for us and for our kids and for their kids. But I'm at least heartened to hear that there is a useful application in your field, Dr. Moolekamp, that is assisting you in ways that it might at least make the work more efficient, faster. Yes?
Yeah, it really, to me, it takes a lot of the boring work. Like it's not going to replace, like scientists because it can't do the creative parts. It can't do the large analysis. But what it can do is just the boring, mundane things that I hate doing. It does. And I love it for that.
That is a great way to describe what we should be doing with AI. It should be doing the boring things, not the creative, important things that, I don't know. Now I'm on a soapbox, and this is not a soapbox hour. We are talking about the remarkable work that's happening at the Vera C. Rubin Observatory and some of the connections right here in our own community. And you heard earlier this hour, you heard Dr. Becky Borrelli, who is Principal Fellow in Space Superiority and Imaging Systems at L3 Harris, talk about this local connection. And now is the work, now that this has been successful, is it done for you? I mean, what else? Is there going to be fine-tuning, additional work for you in the future with this?
Our part on Rubin is complete at this point. Once we delivered the mirror, it was done. But we continue to work with the scientific community on other scientific missions. So we work very closely with NASA. We have multiple missions that we're working with them right now. But yeah, our part with Rubin is completed.
Do you feel that this community should have a little bit of pride given
Absolutely.
our hometown connection
Absolutely.
here?
Not only Vera C. Rubin, but we had a huge part in the James Webb Space Telescope. We had a huge part. We made the telescope for the Nancy Grace Roman Space Telescope, which is at Goddard now preparing for launch. We are partnering with NASA on their laser interferometer space array called LISA. And we also are working very closely with them on their next mission, which is Habitable Worlds. Our connection in Rochester to space science and universe exploration goes back a long way, and we continue to work with those partners.
M2 is the largest convex mirror ever made. Is that correct?
Yes.
Largest convex mirror ever made. And the camera is the size of a small car. And I think if you're watching on our YouTube stream, we've got images up. I want to make sure that I'm describing. I've got a couple in front of me here in physical form, and then we've got them on YouTube here. So this is going to be like kind of a really bad game show, but this is an image provided here by Rubin. This is actually 678 separate images taken by the observatory in just over 7 hours of observing time, and combining images this way reveals faint or invisible details such as a cloud of gas and dust that comprise, I think it's the Trifid Nebula in the top right and the Lagoon Nebula. These are several thousand light years away from Earth. Several thousand light years. Alpha Centauri is how many light years away? Like 4 or 12 or 8 or something?
Roughly 4.
4,
yeah.
okay. These are several thousand light years away. So I'm going to show the room here. Megan Mac, if you can see, there's the one we're looking at here. We're showing it on YouTube. So I don't know. I mean, Segev, what do you see here?
To be honest, it's very easy for me to turn off my scientific mind and look at it with my artistic mind. I see just these beautiful colors, intense bursts of light and dark bands where there's absorption happening. So both the appreciation of just how beautiful the image is, how gorgeous the image is. And, by the way, seeing it at the planetarium a few weeks ago and really zooming in, and it seemed like there was no bottom to the level of detail, was just amazing. And it really brought out the kind of inner 7-year-old in me. Looking at it then and looking at it now, it's incredible to look at. It fills me with wonder. Understanding what some of it is doesn't diminish that at all, right?
I think that's great. And so now go a little more science-y and tell me more when you can set that artistic side
right
aside and tell me a little bit more about what you're seeing there if you're putting your science wonk hat on.
Well, whenever you look at a nebula, you're seeing an important part of the stellar life cycle. You're seeing a kind of stellar graveyard, but also a stellar nursery, right? Nebulae are produced when stars reach the end of their lives and explode, and their atmospheres are blown outward into space. But then that material eventually cools, recondenses, and then as it gets dense enough, it forms the nucleus of new stars. And so we're seeing a nursery, essentially, a stellar nursery.
What are you looking at here, Jim? What do you see?
I see colors. I see scale. So, there's a lot of things that I think the general public, when they see these images, they want to ask. But for me, it is just the fact that it is beautiful, and it makes you want to know more. It makes you want to ask questions. And in this image, on a small scale, you're showing me a piece of paper, but the image itself is enormous. And if you zoom into that image, even the areas that feel bland, around the corners and the edges, you see these oranges and yellows. These are individual stars and uncountable numbers of them. So the more you zoom in, you see so many points of light. It is phenomenal. So it's the scale that image is so far away, but also what's in it and how much is in it, and how you can use those images to get the public interested and excited about astronomy.
Well, the scale part really is interesting. And so how do you help the lay public, whether they're coming for the first time to the planetarium or if they are getting interested in Rubin, how do you help people understand the scale of the universe as we currently understand it, which is an ongoing process? But how do you start to even contextualize our existence?
That's always such a fun stepping stone, because for me, probably the single most interesting thing about the sciences or astronomy is scale, whether it's the tiny scale and you're talking about nano, or you're talking about the cosmology and how big the universe is. So even stuff that appears close to us, you would say our closest celestial body in the solar system, the moon, is pretty wildly far away. You see diagrams of the moon pretty close to the Earth, but in reality, this is 250,000. You could fit all the planets between the Earth and the moon itself. Is pretty phenomenally far away. And that's something that is really close to us, at least is how we would perceive it.
It's right in our neighborhood and in the universe, yeah.
Yeah, and then when you say, like, okay, well, let's extend that to the next star. As you mentioned, 4 light years is 4 is a small number, but when you start breaking that down into miles, it becomes a nonsense number. You would call these astronomical numbers, probably in today's terms, maybe more economical numbers, but regardless, huge numbers. So when you try to break down what it means, that a star 4 light years away, that light you're seeing left the star 4 years ago. That makes all of these some small time machine in a way. The distances you're looking back 1,000 light years away. That's 1,000 years ago. A lot of this light is coming to you from, which is just really spectacular. And finishing that off, I mean, just a little glimpse in scale really gives you that impression that turns out there's a lot of space in space. It's a huge, empty, and wildly, almost unimaginably vast, thing. I don't know how you would describe.
No, I mean,
space.
I think that I mean, even the 1,000 light years, helping people understand that what you're seeing is kind of a time capsule, and that when that light was emitted, we were not sending texts on iPhones.
Yeah.
It was indoor plumbing wasn't really in vogue. It was a very different time, and we're just seeing it now. And it's really remarkable.
That goes so far too. I think what's also wild to me is just imagine, and we don't have any evidence that there is life elsewhere in the universe, but if you could say that there was a wildly futuristic people in the Andromeda galaxy, and they have this impossible telescope that can somehow resolve the surface of planet Earth, and they did that, they would be looking at the way the Earth was, like 2.5 million years. That's roughly the distance to the Andromeda galaxy, if I'm not mistaken. That's wild. So they might be looking at what was happening here 2.5 million years ago, which is, by the way, not what's happening here now. And that, whether you go either direction, that is just, it's mind-boggling. And it gives you so many other questions, which for me is the exciting part. Things we're getting people excited about, just science in general.
I love the idea of thinking about not what we are looking at, but what the dudes on Andromeda are looking at. Because I'm
Once
trying
again,
to,
I'm not saying there's people on Andromeda.
I know you're not. I am. I can say it. And I'm trying to remember my science classes in high school. Australopithecus afarensis, Lucy, was how? It feels like millions of years.
I think it's about right. It's about over 2 million years.
Okay,
Like that.
so it may be the Australopithecus afarensis crew that they're looking at, going like, okay, that's pretty advanced in the universe. Like as far as the universe goes, that would be a big deal. But it turns out that that's just because that's how long the light took, and now we're playing Donkey Kong, and they're like, wow. I mean, the scale, amazing here. Do you? Dr. Borrelli, do you think about scale? I mean, is that part of how your brain sees it? We can show you a separate image on YouTube as well. I mean, this is also, it's got these cool swirls, which I'm not really sure. Fred will tell me in a second what they're. This is the Virgo cluster? Yeah. So what are you seeing here?
It's incredible to look at. We get really excited when we actually get to see images from the systems that we get to work on. And one of the things I like to keep in mind is that while there's color in there, a lot of those wavelengths are ones that we can't actually see. So that color's been added so that we can see it. So a lot of telescopes work in the infrared. We can't actually see that, so artists will shift the color so that it's something that we can see. But every single one of those colors is a different wavelength, and it's carrying information. It's giving us some sort of information about what is out there. If you have something like a spectrometer that Dr. Moolekamp mentioned earlier, you can actually break down the different wavelengths, and you can tell what's in there element by element based on what you're seeing. You can tell how fast things are moving. You can figure out relatively how far away they are. Are they moving closer to you, or are they moving farther away from you? So not only is it just visually beautiful, but every single color in there is giving you different information about what you're looking at.
Fred, what about you? So what am I missing here in terms of this whole conversation, Dr. Moolekamp? When I look at these here as a layperson, what should I be seeing?
Stars and galaxies. No,
That's what it is.
I think yeah. This picture of scale. I think this is a really good kind of topic to expand upon, because sometimes in some ways we can picture things that are smaller. I don't know why, but we can think of if I say an atom, right? Like that has a certain image in your head of how small that is, right? And then the nucleus of the atom even smaller, right? So we think about the nucleus of an atom that makes up us and everything around us we see. And then if we imagine that atom is also made up of atoms, right? And we think about the nucleus of an atom on the nucleus of an atom, the universe is bigger than that, right? And so, so even those images, what we're seeing here is just a tiny fraction of what's really out there. The universe is that big. The other analogy I like to give, so when we had the eclipse a few years ago, my son and I made kind of a scale model of the solar system in our road. And so we set about 200 yards, so about 2 football fields from where the sun is to where Neptune is, right? And so when you do that, so if you do it on that scale, okay, the Earth is just like a couple feet away, right? Like most of the inner planets are just, like they fit in this room. And then like you get to, that's where Neptune is. The nearest star, Andromeda, rather Alpha Centauri, is in Ohio at that scale, which again, is just kind of mind boggling, right?
Absolutely. I love that. Your son's a lucky dude. That's a really fun way to do that. And I am curious to know what the swirls are there. This is really a beautiful image, but what are we seeing with the swirls, Dr. Moolekamp?
Yeah, so galaxies normally have like kind of a bulge part in the middle. That's where a lot of the older stars. The blue that you see there, that's star forming regions. Like essentially, what you can think about is there's gas that's dispersed throughout the galaxy, and then as these density waves come through, which is what the spiral arm is, it's kind of pushing stars together. It's pushing the gas together. And as it does that, it will trigger star formation, not in just like one star, but you actually get this entire population of stars that are all forming at the same time. And those are really hot. You have some really hot, really bright stars. Those are going to be the bluer stars. And so that's what kind of dominates the light that you're seeing.
These images, again, I hope your listeners are able to see them on YouTube or look them up and go deeper with them. It really is a remarkable achievement already, and it's really mind-boggling to think of what is still to come from Rubin with the work that they're doing. And I mean, I'm kind of at a loss for words for it, but one thing that does come to mind, going back to, because I think Jim said there's definitely people on Andromeda, and no, Jim Bader, who is the director of the Strasenburgh Planetarium, did not say that. I did. And I'm thinking about just the scope and the scale that you've all been talking about. And one of the things that's sort of difficult to even conceive of, I understand there's technology and science that would boggle the minds of the smartest human beings, let alone me. And maybe there's energy capacity elsewhere that maybe there are Dyson spheres or Dyson swarms. Maybe that exists, and people can really travel among star systems. Who knows? But the scale is so hard to conceive of that I can't help but conclude two things. It's like there's no way that there's not more life out there, just given the number of opportunities, 10 billion trillion Earth-like stars that we know of, for starters. But also, there's no way we're ever going to be able to talk to it. I mean, it's just so far away, and even the best tech and energy, it's like, how are you getting here? It's very hard to conceive of. But I don't know, Segev, is that too pessimistic?
It depends. I mean, there's a combination of factors that affect whether or not we could communicate with other life out there. Some of the factors that are less related to sociology are actually pretty optimistic, right? So we now know that most stars actually do have planets. That's a result of about a decade of surveys now in astronomy. And so the numbers are very much in favor of some of those planets hosting life. How much of that life is intelligent? How much of it can develop technology to communicate? Is that done in a way that doesn't essentially use up their biosphere in a way that makes their habitat toxic to them? Do they destroy themselves in the process of this? These are all sociological questions that are much harder to answer. And since I'm not a sociologist, I won't answer those. But I would say the astronomical part of the question, the biological part of the question is very optimistic. I'd say there's definitely life out there, almost certainly, just playing the numbers. There's huge numbers of planets, huge numbers of stars.
But technological civilizational life? I mean, because again, that's where the great filter comes in. What is going to prevent something at the cellular level, which would be an amazing discovery on its own, from becoming? I love that we think we're intelligent. Like, I'm sure there's like species out there that are like, oh, that's so cute. But civilizational, technological. I mean, do you think that is definitely the case?
I would never use the word like definitely.
Do you think it is very likely?
I think it's very plausible is probably the most strong word I would use.
Okay. All right. Dr. Moolekamp, plausible?
Yeah, I think so. I think I think even if you think about it from like a physics standpoint, there's kind of this idea, like I'll briefly touch on this idea of entropy, right? And one way you can think of entropy is kind of like the amount of information in something, where like the more complicated something is, the lower its entropy. And in general, the universe tends toward higher entropy. It tends to like, go into disorder and disarray. But we have pockets of low entropy, right? We live in one. We are one. We're, you can kind of think of us as low entropy beings, right? And so I think that there's, because we evolved here, I think there is reason to believe that, there is some other, law that has to do with entropy where you can get, like a, fixed point where you can start to get a decrease in one area by, raising it everywhere else.
I don't know of anywhere else in the universe that we could go and stand outside under the sky and breathe.
Right.
But I think what I'm hearing you say is we evolved here to do that. Therefore, it's plausible to assume that those conditions exist elsewhere as well. Maybe not exactly the same, but in similar kinds of adaptational evolution.
Yeah, I mean, it could be completely different, right? But just the idea that it would still, like, I think mathematically, like, I can imagine it, going toward in finding some way to use the conditions around it to, lower the entropy in those regions.
Okay. I mean, what do you think? We're alone here, Dr. Borrelli?
I doubt we're alone.
No way.
To put a finer point on it, right? We evolved to live in this atmosphere, but there are thousands of species on our planet that evolved to live in a very different environment, which is the ocean, right? We can't go live underwater, but they evolved to do that. So what's to say that species on other planets and other environments couldn't evolve to do that?
I mean, that should be a very obvious point, and yet that's the first time I've ever thought of it that way. I'm always thinking of like, wait, we can stand outside under a sky. Not if you're a fish and we can't go underwater. No, that's a really, really important point. And it just makes it seem, I don't know, Jim, so you got to come to the conclusion, right? We can't be alone.
I think that's plausible. I love that description. Plausibly, we are not alone, just statistically speaking, the amount of stuff that's out there. But I do love the sci-fi of imagining what it could look like. I think not to give credit to Star Trek, but they did a pretty wild job describing how other life forms could exist in other wild environments. Do we expect to go to other gas giants and find intelligent jellyfish type life that have created their own tech, living in the atmospheres of gas planets? What do we find? I like that. That is really exciting and spectacular, and it's the questions of things we don't know what to ask yet.
These poor guests did not expect to come on and get quizzed on possibilities of aliens, but that's sort of one of our hobby horses here. And listeners, if you haven't watched Resident Alien, just a little bit of the plot. This alien species has been coming to Earth for thousands of years, kind of monitoring our species. And they've come to the conclusion in 2021 that we've really just not been useful, that we've become really kind of wasteful and possibly dangerous, and we're at the point where we should probably be eliminated. I mean, they tried to help us for a while. They tried to show us technology in subtle ways and built Stonehenge and did cool things, but now they're like, not worth it. So anyway, it's a comedy, and it's pretty funny. I think the writing could be better, but we're trying to be optimistic. And what a great conversation. We've got to get our only break of the hour here. We'll come back. We'll answer some listener questions if you have them about Rubin. We're talking to Jim Bader, director of the Strasenburgh Planetarium, Dr. Segev BenZvi. Segev is associate professor of physics in the Department of Physics and Astronomy at the University of Rochester. Dr. Becky Borrelli is principal fellow in space superiority and imaging systems at L3 Harris. And Dr. Fred Moolekamp is a research scientist at the Rubin Observatory. Let's take that break. We'll come back on Connections.
Support for your public radio station comes from our members and from Bob Johnson Auto Group, proud supporter of Connections with Evan Dawson. Believing an informed public makes for a stronger community. BobJohnsonAutoGroup.com.
All right. During our brief break, Segev educated me on something I'd never heard of before, so make sure the audience understands the galactic quarantine theory.
Well, it's much more of a joke than a theory.
It's not
right?
a theory,
but
no.
This is something that exists in pop culture where we have not seen evidence for extraterrestrial life because we've essentially been examined by an advanced galactic civilization, found to be wanting, and are now kind of cut out from the rest of galactic society.
So, ostracized, ignored, put in a corner.
Yeah,
just not worth interacting with the cool, actually smart crowd.
Right.
Okay. Is that plausible to you?
No, it is not. I don't think.
It's really funny though.
Yeah.
Yeah. I mean, lately it's really feel like it's more plausible by the year. But anyway, that's a fun one to think about here. CY writes, in his Dark Materials, Philip Pullman envisioned a device his character has used involving quantum entanglement, in which two atoms were entangled so that when you manipulated one, the corresponding one would respond identically wherever it was in the universe, and they used that to communicate. Fiction, but still a wild concept. Fiction, yes. Also implausible?
No, quantum entanglement is a real thing.
What?
Absolutely. Being tested and used every day. And yeah, that's absolutely true. It's you can entangle two particles and have them interact in what's called non-locally, where you affect one part of the system and then it appears to instantaneously affect the other part.
I mean, how do we have that on one hand and throughway rest stop bathrooms on the other? What an amazing species we are. We're an amazing species. See why? That's awesome. I had no idea. Dallas is asking, if we plan a trip to Andromeda and we start flying there, could we find out, it's gone? I guess, yeah. I mean, I guess, I'll start with Jim because you're the one who really thinks we should go to Andromeda and talk to people there. But wherever we would go that's light years away, it is plausible that something happens in the interim.
Yeah.
And we are eventually arriving at a very different scenario, right?
Yes, certainly possible. I think, and I'm curious how other people would agree with that, but probably unlikely that Andromeda is gone. But it certainly could be pretty different, or not what you'd expect, and that would apply to, anything that you see moving on a day-to-day basis. When you get there, if you see a baseball, it is moving. You get to it, it might have moved a little bit, and the same thing would be the case with Andromeda. Stuff won't be in the same place. The galaxy is moving and churning. That simple idea alone. But yeah, what else would you find when you go out there?
Yeah, so if we find biosignatures on exoplanets and we go, well, that's 80 light years away or 50 or 40. I mean, it's better if it's closer for a lot of reasons, energy-wise, wanting to be alive when you get there, all kinds of things. But also just hoping that it's unchanged, or I don't know how much we can observe by. What do you think there, Segev?
Well, I would say stars are incredibly long-lived, and species are incredibly long-lived. So we have good reason to believe the human species of order 100,000 years old. So if we're talking about travel times that are under 100 years, the odds are in our favor that things will be okay.
No, I think that's pretty good context there. Anything this side of the table you want to add to the context? Should be closer. Unfortunately, I don't think there's anybody hanging out in Alpha Centauri. But
yeah, I mean, I guess as the crank of the panel, I'll say that. I think that we also have to be careful when we imagine, again, 2 million years ago when you had the first, human-like species, right? Could they have imagined communicating with, anything outside of eyesight, let alone the other side of the planet, let alone knowing there was another side of the planet?
Right.
And so you just never know what we're going to discover, right? There's weird things like wormholes and things that are, scientifically possible. And then that even changes, the travel time, right? If you can all of a sudden kind of poke a hole in space and go in one place and out the other, then you don't have to traverse the entire distance around. So, and I'm maybe more optimistic about wormholes than other people, just because people used to think black holes weren't real. They were just this quirk of the mathematics that kind of came out. But it seems like every time there's a quirk in the mathematics, we find it eventually. And so who knows, where that could lead.
Quirks in mathematics are like a fiction plot's Deus Ex Machina, where it's we're just going to go through a wormhole like they did in Interstellar. But it turns out maybe
yeah.
Yeah. Okay. Yeah. Anything you want to add there, Dr. Borrelli?
No, nothing to add.
Okay. Here's a really good one from Mike. He wants to know, how can the universe be both infinite and expanding? That's a great question. Do we think it is? Anybody want to jump in first on this? Is that what it's? The universe is expanding. We know that, or we think we know that, right?
Right. Yep.
So, is it all? Can it be both infinite and expanding?
Well, this question goes back a couple hundred years, actually, where people ask this question: is the universe infinite? Right. does it not only in space but also in time, right? Was there a starting point or not? And the answer that we have now is that we do believe it's finite. We do also believe that it is not infinitely old. The question about the expansion, what is it expanding into, is maybe a bit of a difficulty that we just have imagining what's actually happening, because we imagine the universe as some sort of object embedded inside of a larger object, but that's not necessary to understand that it's expanding. So, much in the way that we're evolved to understand and think about three spatial dimensions, and you can add a fourth to that mathematically. There's nothing wrong with that, but then try to imagine a four-dimensional object is impossible, right? We start to struggle to come up with a good metaphor for what's happening when we're talking about the expansion of the universe, right? It's not embedded in some sort of larger structure and filling up a volume that we're not accessing.
But it's a really good question.
Yeah, it's a really, really good question.
Because it probably does demonstrate the limits of our understanding, Michael. But I mean, for me, again, I go back to a college professor, a religion class, who talked about, I think this is way back at Ohio University, but he talked about the postulate of first cause. And he said a lot of faith systems start with this idea of trying to go back to everything's got a cause and effect, how far back can we wind this? But how do you have an effect without a cause, or a cause without, the postulate of first cause is kind of the God of the gaps, and I'm not belittling religion whatsoever. I'm just talking about how limited we are in our thinking, and how I think it is very understandable to start thinking in different ways. For some people more spiritual, for some people in different maybe scientific directions. But it's a really good question. Dr. Moolekamp, anything you want to add on expanding and infinite?
Yeah, I think it's hard to say, again, whether or not it's infinite. We seem to think that it's not, but it's kind of like like we used to think of like the universe as the stage and people are the actors. But it's more like everything in the universe is part of it too. Like what makes up the universe is the things inside of it. And so trying to imagine what's outside of it, this is like, at night when I'm having trouble sleeping, this is the kind of thing that I try to do and picture, and my brain just eventually blows up when I fall asleep.
That's amazing. The scientist having trouble sleeping, and it's amazing what you would be thinking about. It's very different than me. But as we get ready to wrap here, I got an email just asking kind of what Jim was saying at the outset of the program, or even before the program, which is what we're seeing at Rubin is going to impact people in everyday life. And it's easy to kind of convince yourself that it's a conversation for one crowd. But let's just kind of close with this. What are some either everyday impacts or big questions that you would, maybe optimistically hope that Rubin down the line can help answer?
Well, I love that it had, these beautiful images having impact outside of what you would expect. Obviously, you expect a group of people like us who have physics backgrounds and astronomy backgrounds and engineering backgrounds, but what about everyone else? And a good example for me is just the most direct art. It's a beautiful image. You look at it, you can certainly think about how many stars and galaxies you see in that image, or what's happening in that image. But, how does it make you feel? The colors, all of this has an impact. And you see this happen from other beautiful images from other observatories. And I think I have a really great example from the Hubble Space Telescope and its ultra deep field. So it's a beautiful image that holds a ton of galaxies and a handful of stars specifically that you can see. But there was an artist who kind of remade this. I think his name is Dario Roblito. This piece is actually at the AKG in Buffalo, but he took stage lights that you'd find on a theater stage and put these on black backdrops. And if you see that image, almost instantly, my brain says, oh, what is this ultra deep field variant of some kind? But it's art that was inspired by these types of things. So this impact has a ripple that affects many other communities that maybe most of us, especially in the sciences, our brain doesn't immediately jump to, how could I create a beautiful piece of art from this image? We might think about what it means in that image. And I love that.
Well said. Hey, you got about 20 seconds. What's a big question that might get answered thanks to Rubin?
How fast is the universe expanding, and what is it going to evolve into? I hope.
Those are big ones.
Yeah.
Dr. Moolekamp?
Yeah. How? I guess I kind of already said, like, how is dark matter distributed in the universe? We should know that.
What's exciting to you? What kind of questions are you hoping get answered here?
Honestly, a lot of times I find it interesting to see what we didn't expect to find, right? There's always something that comes up that surprises all of us in this field. And the other thing is, with these types of systems, the engineering and the technology that goes into them are typically first of their kind. And seeing how those things evolved and are used in other ways and in other systems, right? Google Earth satellites, they're taking pictures. We use them for mapping all the time. Those technologies existed because of systems that came before them trying to do scientific missions and things like that. So seeing how the technology evolves, seeing what we find that we don't expect is exciting.
Oh, well said. As we close here, Jim, how can people engage more with what we've been talking about here at Strasenburgh?
Well, you could definitely come by almost any of our shows. We're going to have new images from Rubin as we get them. We certainly every day explore images that have been released. It's beautiful, and they are enormous. Only experienced from places like the planetarium.
Great place to do it. And anything else, other guests, for people who want to kind of keep up with the work of Rubin? Anything that the public can do to do that?
Yeah, we do have a website, and there is a sky viewer that you can download on your phone, an app, and you can actually look at the images and zoom in and play with the data. There's even citizen science projects.
We'll try to see if we can link to that in our show notes. That's a great idea. Thank you all. Congratulations on the incredible success here. And I want to say, on behalf of our audience, thanks for being great communicators to the public. You do such great work. Thanks to all of you for being here. Thank you very much.
having us.
Thanks for having
More
us.
connections coming up in just a minute.
This program is a production of WXXI Public Radio. The views expressed do not necessarily represent those of this station, its staff, management, or underwriters. The broadcast is meant for the private use of our audience. Any rebroadcast or use in another medium without expressed written consent of WXXI is strictly prohibited. Connections with Evan Dawson is available as a podcast. Just click on the Connections link at WXXInews.org.